In order to make sense of what water does in the atmosphere, we need to understand the three physical phases of water. In fact, the three physical phases of water is the same three physical phases of matter, and you'll find this in an earlier chapter on physics. So water can be a solid, we call that ice. Water can be a liquid, we call that just simply water. Or water can be in its gaseous state, which we call water vapor. Now, one of the cool things I think is that like you saw in the previous lecture, that there is water vapor everywhere, and it can be, well, say not if your room or your environment's very dry, then there's no water vapor, but water vapor is with you now, I assure you. So we talked in I think we talked in physics about different types of energies. We have potential energy and kinetic energy. And kinetic energy is the energy associated with motion. So one of the things I want to assure you is that all matter has motion. It may not look, for instance, if you're looking at a table, it may not look like that table is moving, but at a molecular level, atomic and molecular level, there is motion to the molecules and atoms that make up that table. So we say, and I'm not going to be able to necessarily animate this for you, but if I look here, and this is my solid, this is my liquid, and this is my gas, what this is trying to show you is that all matter has motion, and motion is associated with what we call kinetic energy. Now, if I were to show you, focus on the solids, and I was to show you how much motion they have, I'd make like a little arrow. So that's kind of like a little arrow going back and forth. Now, if the length of the arrow is an indication of how much motion there is, when I go to liquids, I'm going to make a bigger arrow, okay? Now, notice then also that the liquids are kind of spread apart, and we're going to talk more about this in the next slide. They are less connected. There are fewer what we call intermolecular bonds, and there's more motion. Now, gas particles are my favorite. I love gas particles. Gas particles basically have no connection to each other, and they have a lot of kinetic energy. Lots of Ke. Lots of kinetic energy. Another way to say that is they are moving very fast. Moving fast. Okay, gas particles, whether that's water gas particles, water vapor, or whether that's oxygen and nitrogen in the air. That is so cool. So to focus on just cute little molecules of water connected together or not connected together, all matter, well, molecules, I guess I should say, are generally connected with what we call intermolecular bonds, or IM, intermolecular bonds. Now, water is special in that the bonds that connect water molecules to each other are actually called hydrogen bonds, and they are especially strong. So keep that in mind. Let me kind of show you what hydrogen bonding in water molecule looks like. I think this is coming up. I'm just going to kind of fast forward. So a water molecule, if we were to draw the Lewis structure, remember Lewis structures of a water molecule, it would look like this. So I have an oxygen, hydrogen, there's my H2O, and then the oxygen actually has 2 lone pair electrons. And I think we talked about electronegativity in chemistry. And as it turns out, the oxygen atom is highly electronegative, so it's what we call partially negative. And the hydrogen atoms are partially positive. So it's what we call, has a high degree of polarity. So that kind of sets it up for if there's another water molecule in the vicinity. Here's my second water molecule. And it also is partially negative, partially positive, partially positive. So here we go. We have these intermolecular bonds between, I'll go ahead and draw them in green dashes, between the oxygen of one and the hydrogen of another. Okay, it's almost like playing Twister. We could have this hydrogen and this oxygen, and of course we would have more molecules over here. This figure, I believe it's from your textbook, is actually kind of showing you that hydrogen bonding. So can you see the red are the oxygen atoms and the white are the hydrogen atoms, and you can kind of see them bonding to other water molecules. The partially positively charged hydrogens bond to the partially negatively charged oxygen atoms of another molecule. So one of the things we need to talk about is phase changes, and it happens all the time. All phase change is it's changing, in this case, for instance, from a solid ice to liquid water. And if I were to ask you, you would tell me, well, I need to add heat in order to make that happen. We can actually quantify that heat, and that heat is actually what we call the latent heat. Anytime you're using heat to melt something, that's actually latent heat of melting, sometimes called fusion. Okay, now like I said, these hydrogen bonds are extra strong, so this latent heat of melting is a fair bit. And then, of course, then on the product side, we have liquid water. So liquid water here, hopefully you can kind of see the if you were to look at some of these bonds are broken. That's my point. We break at least some of these bonds, okay, to form liquid water. Now, one more thing before I leave this. Does it look like this is, I call it fluffy over here? My solid looks more fluffy. And it is. It actually takes up more space. Because it takes up more space, it's fluffy. Actually, it has a lower density. Water has a lower density in its solid form than it does in its liquid form. So this is more dense. And thank goodness for us that that's the case, because if you, well, not just because of this, but if you get a cup of water and you have ice in it, you're going to actually see your ice cubes float up here. That's because ice is less dense. And on a larger scale, if you look at the oceans, okay, associated with the oceans are these, this is my iceberg, okay. Thank goodness that the icebergs float, because if they all sank, okay, they would displace the water and we would be in trouble with regard to levels of water. One more thing then in this, before I go on to the next part. So I told you that if you melt water, or excuse me, if you melt ice, well, you know, if you melt ice, you have to add heat, and that's called latent heat, okay, to break the bonds. And so to break at least some of the bonds. Now, we don't want to break all the bonds, or we're going to end up with a gas. So this is like called an energy diagram. So you can kind of think of this as time, okay, and also time and energy, because we're going to keep pumping energy into this system. What is this system? Well, we have a solid ice here. So all this is saying is your ice starts out at a very cold temperature. We have temperature along the y-axis. Very cold. We pump it, pump it, pump it, pump it, and our ice will actually warm up to the melting point temperature of water, which is 0 degrees. And then at 0 degrees, it will melt, 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 melt. And does it all happen at once? Well, we kind of take it as doing that. It will all liquefy. Here it is in the process of being liquefied. And then after it liquefies, we keep adding heat, and now our liquid will heat up. And here's our liquid warming up to a temperature right at the boiling point temperature of water. Let's see, what else do we have on this slide? Then, speaking of the boiling point temperature of water, if I were to take this water, which is now at 100 degrees Celsius, and I were to add more heat to it, what's it going to do? It's going to boil, right? Then at that point, actually, it's going to go from a liquid to a gas, okay? And that heat actually is called the latent heat of evaporation. Make sense? I think so. So, I forgot my builds were like this. So here then we have kind of the rest of the story. We have our liquid transitioning to a vapor right here. We're pumping energy into it. It's holding at the same temperature, 100 degrees Celsius. Then if we keep pumping energy into it, what's going to happen then is that gas is going to raise in temperature. And actually that's what you see here. So that's called an energy phase diagram, I guess, of sorts. And I've been talking about the amount of heat required is all called latent heat. So we have the latent heat of melting and the latent heat of evaporation. Okay, now this is a little less intuitive. If we go from what I sometimes say right back to left again, if we go from, if this is my solid, liquid, gas. If we go this way, of course, that's called condensation. And if we go from a liquid to solid, that's called freezing. Now, I bet you buy this that in those cases, bonds are formed. And as bonds are formed, energy is released. Energy is released. Now, take, for instance, you're making ice cubes. How do you make ice cubes? Well, you take liquid water, you put them in your freezer, and actually you draw the heat out of your liquid water, so energy is released by your liquid water in order for it to freeze. Okay, those are then latent heats are associated with those. So bonds are being formed when, for instance, I have here condensation. Hopefully you're kind of familiar with that term. Now, in meteorology, we're going to have to use that term a lot. What does condensation mean? It means gas is going to form a liquid. It's condensing. Freezing, of course, I hate freezing. I hate snow is bad, but ice is even worse, right? Oops. Okay. That's freezing. And bonds are formed and energy is released. And I didn't mention this on the previous slide, but I'll go ahead and try to kind of mention it now. Deposition is when it skips the liquid stage. So here we go from a gas straight to a solid. And my favorite example of that is frost. Consider frost. What does that look like? Well, you wake up in the morning and your grass, instead of having nothing on it, if it doesn't have dew on it, but if it's too cold, the water has gone straight from being water vapor in the air to solidifying to form grass, or sorry, to form frost. I didn't mention it before, okay, but on the previous slide, when something goes from a solid straight to a gas, we call that sublimation. And my favorite thing is if you get dry ice. Okay, what is dry ice? Well, it's not water, but dry ice is CO2 solid. And the cool thing about dry ice is that it will go straight from being a solid to being a gas. It skips the liquid stage. I just think that is so cool. That's called sublimation. So here I've got kind of a summary of what we've been talking about. Not sure what page I'm on here. We've been talking about phase changes. And we said that these are things you're already familiar with. So I kind of tell students, don't make it harder than it is. A solid goes to a liquid. We call that melting. It requires energy. So this is add energy on this side. Liquid goes to a gas. We call that evaporation or vaporization. That either one would be fine. I talked about sublimation. That was like solid CO2 going to form a gas. We're all adding energy. Over here then on the right, we have these are where energy is released. And these phase changes, and these are very important in the atmosphere. Energy is released during condensation. Now, when we talk about everybody loves the whole severe weather, the thunderstorms, okay, condensation happens within a cloud. Clouds are nice and fluffy because basically they appear white and fluffy because gas has condensed to form a liquid, and a lot of energy is released. Energy is also released when liquid goes to form a solid.